All right, so today we're going to talk about requirements, requirements in particular that we're going to talk about in two parts here. First of all, the basics associated with requirements, and then a second lecture, which is associated with how you actually write requirements so that they are effective. And so here's an outline of the first talk that we'll do. Remember that these are all on the Student Balloon Course website. So requirements, and in my experience, as well as the experience of almost everybody else involved with NASA projects, these requirements are the single biggest cause of project failure. All right. Requirements which are not done correctly, thoughtfully, and completely, basically will drive a project in unknown directions, and that team will have lots of difficulty trying to recover from that. Um, these requirements, when you write them, they basically drive almost everything. They drive the cost, they drive this design, what skills are required, verification plans, operational procedures, the kinds of things that you'll need to put in the payload, et cetera, et cetera. They drive everything. So it's important that one spend time developing the project requirements. So what is a requirement? Well, it is a statement of something you want or need, or it's a characteristic of something you want or need. That requirement is a contract. It's a binding contract statement of that desire of what is needed or wanted. It is a documentation of the issue or the problem space. And it is something that is used to communicate so that there's mutual understanding between all parties as to how that project is to proceed forward. Now, the importance of getting these requirements correct is illustrated by this plot. That this is a typical sort of time versus cost profile of a project. So earlier in the time is when one proceeds with developing concepts and the requirements, and at that point the cost investment. This is not only in dollars, but it's also in personnel time investment or supplies or any other things that goes into making the project. So that early stages, there's very little cost incurred at that point. As you go on through the detailed design and into production and operation, obviously the costs go skyrocketing. In fact, most of your costs for a project are incurred later in the project. Now, when costs are committed, all right, is relatively early in the project relative to when you actually charge those costs. So that's what this project shows, is that early in the project you may not have incurred more than 20% of the costs, but you've committed because of the way that you have developed your design to more than 80% early on, all right, even though you may not have expended those. So that has implications in terms of what your requirements will drive in terms of your project later on in the timeline. So, for example, here's another way of looking at this, and this is like the cost of recovery. So you make a you're going to have an issue. You make a bad decision. That happens. But the cost of those bad decisions, again, in terms of time or dollars or whatever, goes up the further along in the project that you go. These are the different project phases, from requirements through design, fabrication, and finally operations. And as your cost, and as you proceed through your project, your cost of fixing a problem goes up, because you can easily understand this if you're getting into the final phases of the project. making a change at that point is going to involve a lot of moving and shaking. Whereas in the beginning, it's not that much of an expenditure. So again, spending the time to develop and understand and specify your requirements in the long term uh, pays dividends for your project. So where do you get these requirements from? Well, there's several ways that you can get it. Um, so stakeholders, customers, people who are interested or invested in your project, like for example, the LASIS management. Obviously, we are going to fly you, so there are some requirements that we are going to define onto your payload. You already know what some of these are: weight, the distance between the stars going through your payload, et cetera. Those are requirements. Okay, they're derived from environment around you. You will obviously have some goals and objectives. Those goals and objectives are also going to drive your requirements. If your goal is to measure temperature as a function of altitude, then obviously you're going to have a requirement for a temperature sensor of some sort, amongst many other things. All right. You may have some assumptions, or you may have a concept of what your operations are. These are all things that can get from your scope of what your project is. There may be trade studies that you do, comparing different types of sensors that may do the job will set and determine what some of your requirements are. And there's probably a hierarchy. There's probably higher level objectives which drive into requirements, which then flow down into subsystems. So there's a variety of places where these come from. So this is not so much your concern, this slide, in terms of organizational or government regulations, but it exists, and you need to be aware of these things. I mean, where it might derive in terms of some of your outside regulations might have to do with, like for example, in the COVID times here, travel. There's probably restrictions or requirements on your travel, and that may drive some of the things that you do for your payload, like get your payload ready early. All right, so a variety of things like that, but not so much important in the details of the way you put your payload together. So developing those requirements is an important first step, and in fact is probably the most important first step. Um, you need to determine what your goal and objectives are, and from those that flows down into some of your requirements. When we talk about a hierarchy, there are probably requirements that need to flow down into your subsystems in a traceable manner. There may also be some negotiated requirements, okay, to make certain that your system design is balanced in terms of cost and capability and time investment. Poorly written or unverifiable requirements are trouble. I can tell you from experience of doing these kinds of programs for over 15 years that the teams who do not spend time in their requirements and goals and objectives are those very, very likely to fail. So there's a variety of ways that you can what are called decompose your requirements. Um, you can flow down these requirements, and that is a sort of a direct statement about how your subsystem must respond to that requirement. So the example here is that there are requirements for spacecraft communications, maybe entirely flow down from the spacecraft system requirements to the spacecraft system subsystems. Okay, so there's a straight flow down on that. And I think we'll give an example of this a little bit later. There's an allocation, all right, requirement. So a good example of an allocation is that the total weight of your payload is required to be 500 grams. Well, you've got several subsystems in that. You've got an electronics, you've got a power, you've got a mechanical, etc. So what is your allocation for each one of those subsystems? There would be a limit placed on the weight for each one of those subsystems. So that would be a allocation. Then the last sort of decomposition is what's called a derivation. Um, and it depends upon a specific implementation. So here's a couple of examples. Car may have a 0 to 100 kilometers per hour performance requirement used to establish a requirement for a maximum mass and a minimum horsepower. So so you've got one set, and this is very common, that you have other kinds of requirements on this. Many times when we talk about systems and system design, I will make a statement that your system design and your requirements sort of go hand in hand. And this is one of the reasons why, that you start off with a requirement about measuring the temperature as a function of altitude, but that is going to have a derivation to subsystems, like what is the accuracy that you'll need to, how many times per minute will you need to take a measurement, et cetera. So those are all sort of derived requirements from that fundamental requirement. All right, and one of the best ways to keep track of some of these things is through a traceability matrix. And in fact, I'll show you that in your document templates, your PDR and CDR documents, there is a traceability matrix, which basically shows how your requirements are flowed down through your subsystems and how your design and capability of your subsystem meets those requirements. So we'll do more about that later, talk a little bit more about that a little bit later. But there are different types of requirements. So a functional type requirement. So that kind of requirement defines what an item shall do, okay? And performance is how well that item must accomplish the particular function. Then there are constraints, like for example, the current constraint I just mentioned about 17 centimeters between your string tubes, or your total weight of 100 grams. Those are the constraints. And then verification. So how well can your performance and functional requirements be met? Okay. All right, so here's a good example of a requirement distribution. So you can see here, so one higher level requirement then flows down to other lower level requirements, et cetera. So if we start over here, so there's a system functional performance requirement. The crew exploration vehicle system shall provide two-way voice communications during crewed operations. Well, applying that to the flight segment operations requirement document, there's two such requirements that flow from that. Flight segment shall provide voice communications through TDRS. All right, and there's probably other requirements. Well, that flight segment providing voice communication through TDRS flows down into more detailed requirements. Flight vehicles shall provide 4 omnidirectional antennas. Flight vehicles shall provide 2 S-band transponders. Flight vehicles shall provide a switch matrix, blah, 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 blah. And then, for example, the omnidirectional antennas flows down into detailed fabrication elements about exactly what is to be provided. So this is exactly how I just talked about, that your requirements and your system designs flow from each other and feed back to each other, and that it flows down into the details of how your payload is actually developed. All right, so this is a warning slide. So you have a set of requirements up here which are called parent requirements, if you were, and those things are going to flow down to your subsystems as to what they are. However, if you don't produce those parent requirements correctly. If those parent requirements are incomplete or incorrect or conflicting or ambiguous or whatever it is, then the children are going to be that way too. So it just flows through your whole system if you don't spend the time up front in what your requirements actually are. All right. Also remember that in addition to sort of functional or performance or that sort of thing requirements, there are interfaces between your systems. So for example, software is going to have an interface to your hardware, right? It's going to have the ability to read an ADC, or it's going to have to have a capability of flipping a switch underneath command under certain, those are interfaces. Likewise, you're going to have a power interface. You're going to have other kinds of signal conditioning interface. You're going to put a sensor to connect up to an ADC possibly, right? So you're going to have interfaces between these things. So you're going to have those requirements on the interfaces. So a really good example of such an interface is the fact that that a little single board computer like a Arduino Mega, the digital I/O lines there are using what is called TTL levels. All right. Now, if one wanted to communicate with a different kind of computer, you probably need to have a interface which would translate those TTL signal levels to RS-232 signal levels. So that is a interface that you need to understand and be able to define if it is needed for that. All right. So there are a number of documents which, as one goes into projects later on in career, that you're going to be involved with. If you do these kinds of things, you don't have to do these here, but there are things which are called like interface definition documents or interface requirement documents, or the interface control document. Sometimes the interface control document is useful in a LACES program. It define the interface control document basically defines the specifics of an interface. So it allows two groups to be sort of independent of each other, as long as that interface control document is correct. So for example, if you define the interface to the sensors correctly, then electronics can go through and produce all the signal conditioning interface circuitry, and software can go through and develop the programs that would acquire that data. And they don't necessarily need to be in the same room or the same building or even the same state, as long as that interface control document is correct. So sometimes the ICD can be important. Okay, so just in summary, this is what we went through right now. That requirements are important. They define what it is that you're supposed to solve and establish terms by which the mission success will be measured. Without spending the time on those requirements, you can get into lots of trouble with your project. So you really need to spend a adequate amount of time understanding these things. Requirements are distributed throughout your system into your subsystems. There is a way to trace how your requirements are distributed so that you understand whether or not your subsystems are doing what they should be doing, et cetera. So that's basically where we are.